All right. So it's really great to see so many of you here. I honestly didn't expect to get so many people since this is the 8 a.m. talk. To be honest, if this was an academic conference and your talk is at like 8 a.m., you might just as well talk to yourself. So I hope that either you are morning people or you're really excited for this topic, which I think is a really exciting topic. So maybe before we begin, how many of you are working with software, are writing code? Maybe a quick show of hands. All right, okay, that's basically all of you. So in that case, it might very well be that all of this research has already affected your daily life or will so in the future. So I'm really excited to talk about this. All of this is research mostly done at Princeton University, even though now some of our team members have also gone to Stanford or to OpenAI. So, but it's all research, not trying to sell you anything. All the software we show is open source. You can play around with it yourself. You can read our paper, even though it's mostly outdated by this point. So this will be like the big update. Basically, 1 year after we published this paper with a similar title, which got a lot of stones rolling and brought to you the first software engineering agent. So a quick note on the structure of this presentation. Since this, my background is academic, we're going to start with what to measure, which means talking about coding benchmarks, especially one called SWE-bench. Then there's going to be a brief section on agent basics, what's an AI agent, and like what are the variables that go into building one. Then the third chapter is our agent, SWE-agent, software engineering agent. And finally, I'll talk about training language models to be better agents, and also what's next in coding systems with AI. So also, if you have any questions in the middle, just raise your hand, even though you'd have to probably shout to get the question to me. I hope there will be time for questions at the end. Also, there's going to be some live demonstration of SWE-agent in the middle, so you can already place your bets on like whether that's going to work or not. But with that being said, let me just jump in. All right, so let's talk about benchmarks. And one of the oldest coding benchmarks in AI is, or one of the best known coding benchmarks is called human eval. And what you have is basically, you have this little Python stub solution, you have an input variable, and then it tells you, basically what that function should do. And the solution to that, is to put in the function body. So this is what people have quizzed AI to do. And this is an excellent benchmark because you can evaluate it very quickly. You just give all of these problems to an AI, you wait for whatever it writes, and then you just run unit tests to check if it's correct. So this is also very on point for like when you want to test it for autocomplete, for example. Because if I'm going to write this function in my code editor, and I've already like maybe filled in the doc string, it would be really great if whatever AI I have running in the background can just complete the body. So very well-known benchmark, really great benchmark. However, it's also, it got saturated really quickly. So, like already like maybe 2 years ago, or certainly 1 year ago, all of the AI system were at like, 95% plus. At which point, you could say like, okay, maybe this problem is solved, or at the very least, adding even more small percent points on top probably doesn't correlate so well with user experience. So you could say this was easy. And one of the reasons that it is easy is that there's relatively little context in there, right? So this is like a very, self-enclosed problem. Like I don't need to know about any other files. This is all kind of contained just in this doc string. However, since we already called and we are all software engineers or people working with software, you probably have the same experience that most of your time is not really spent, writing software as much as it is like reading other people's code, reading through large code bases, thinking a lot about things, and then sometimes we might spend a day and we only change a few lines on a very big code base. So the story of agents for software engineering really starts with what do software engineers spend most of their time with. And if we model a little bit this process of software engineering, like especially if you're like working on a big project or an open source project, oftentimes you have a really big existing code base, and at some point someone finds a bug. So like maybe they erase a GitHub issue, and there's one example here on the screen. And at first, like if it's a bug report, you might be like, I don't know, works on my machine. And then people, like double down, and you're like, okay, I guess I have to look into this stuff. So, you start by reading code. You start by trying to reproduce the problem. And at some point, you'll probably have reproduced it, and hopefully you've narrowed it down to where the problem is coming from. And so you make some edits, and then hopefully you test them that they really resolve this. Except that this is kind of the very idealistic case, and in reality, and then you're done. In reality, it looks more like this. You're just, wildly trying stuff. You're reading, then you're editing something. You're trying to fix the problem. Maybe it fixed it, maybe it didn't. Anyway, you probably have to, iterate through this whole process. So this is really complicated because there's a lot of steps with that. And SWE-bench, the benchmark that I'm going to start this talk with, basically tries to capture this process, or tries to give problems that usually require such a complicated process to be solved. And then we're going to task AI systems to do the same. So the way this benchmark worked is actually relatively simple. So we basically crawled GitHub for a lot of repositories, starting with the most popular Python repositories. And essentially, we collected pairs of issues and the pull requests that belong together. And when we now try to get an AI system to solve the same, we basically give whatever AI system we have, we give it the issue and the entire code base at the point where this issue was first raised. Then we have the language model do some changes to whatever it wants to do, really. And after it has done that, it basically gives us also something like a pull request, but in reality, it's just file changes. And then the trick with this benchmark is that we evaluate the solution from the language model by running the same unit tests. And basically, in the initial crawling phase, to build this benchmark, we looked for pull requests that introduce new tests that weren't passing before. So we can test that at least, like some of the unit tests flip from failing to passing. And that's how we validate that the language model really solved the issue. All right, so it's all real GitHub issues. It's real GitHub issues from top Python repositories at GitHub. For example, Django is actually a big part of the benchmark. And we validate it with the unit tests that come directly from the pull request that were called itself. So we can, actually, you might have questions about this. So, like there's lots of, subtleties about this, and maybe sometimes the coverage of the unit tests is not so great, and sometimes they might be overly specific, and so on. So it gets tricky once you look in the details. But in reality, in essence, it's still basically just that. All right. So first of all, real-world GitHub issues, and second of all, this is super challenging for AI systems. Especially it was, like 1.5 years ago when this first came out. Basically, 1.5 years ago when this was published, I think the baselines were like 3 or 4% that AI systems could solve at that time, which was so low that people didn't even really want to work on that because they were like, okay, this is hopeless. And the reason that this is so difficult for language models to work on a problem like this is, first of all, you have an extreme amount of context, right? So we're basically passing in the entire code base. Doesn't mean that we just, like dump all of this into ChatGPT, but the entire context that the language model has to explore in some way or the other might be hundreds of thousands of lines of code. So that's a lot to take in. Then it's a reasoning-heavy task, right? So, most programs try to solve some more or less complicated problems, and you have to reason your ways through it to understand it. And also, if we think in terms of agents, there's an enormous action space, right? So even though the tools that we'll give to the agent in the end will be super simple, just the fact that there might be 1,000 files, and then once I get to edit a file, I can write arbitrary words in that, right? So it's not like it's the exact opposite of let's say a multiple choice question where an AI has to decide between 5 things. Here you can literally do, you can write books, you can do whatever you want, right? So this combination of having an extreme amount of context, of requiring reasoning, and having this very large action space made this benchmark really, really hard at the beginning. However, now 1.5 years later, it looks very different, and we are starting to even saturate this benchmark. So this is basically the revolution that took place in the last 1.5 years. So there's a few spin-offs also of this benchmark that I'm mostly mentioning. If you already are familiar with SWE-bench itself, we try to extend this a little bit to what we call SWE-bench multi-model, where we have front-end issues. So not only here, we had a little bit of an issue text, and we had the code base. But then when you're doing front-end design, oftentimes your bug reports might be more like screenshots, someone takes a screenshot of a button and the button looks wrong or something like that. And so we wrote the second benchmark where every single issue actually has a screenshot or has some kind of image associated to it, which might be complicated diagrams, it might be maps, it might be here, this is a syntax highlighting project, and the syntax highlighting is wrong, and so on. So this is even tougher than the original benchmark, but still the best systems right now get 25% correct. And if you just look at the development in the last year, so here, a little bit of a complicated diagram, but basically we're going to look at gray versus orange, where gray was May 24, so that's basically 1 year ago, and this is a few months ago. So within 1 year, language models went from, for example, here from 23% to 58% of all the issues in this benchmark solved. So we more than doubled it. And these 23% were also up from just a few percent points a couple of months earlier. And so also this plot is now a few months old, and ever since Claude came out with Sonnet 4, I think we're looking at the high 60s to 70% here. Meaning that from all the GitHub issues and pull requests that we crawled 1.5 years ago, the AI can now, in almost 70% of the cases, solve them, as in it produces a solution that passes all the unit tests. So this was an insane amount of progress, and I think it absolutely demonstrates that in the future, autonomous agents will solve a lot of our issues and bugs. However, I should also caution that this number is a little bit hard to interpret because, of course, it's a curated data set, right? I mean, we just crawl all the issues and pull requests, but just by the fact that they need to be self-contained and they need to have these unit tests, it's still a somewhat biased selection because all selection, necessarily induces some bias. Also, it corresponds to, it's a mix of different repositories, and the solution rate between these different repositories, they are quite different. So even though this is kind of an average, if you apply it to your own project, depending on what you're doing exactly, you might see different numbers. They might be half or they might be higher. It really depends what you're doing. For example, I think if you're doing something that has a lot of mathematics in it, probably AI is not so great at that. It really depends what you're doing. But still, I would say, if you take an average GitHub repository with a large user base, that we get very well-formatted, very complete issues, it might very well be that right now we solve 50 to 60% of the issues. All right, any questions to benchmarks? Because I think I'll jump to agent basics. We also will have time for questions later. Good. So let's talk about how to solve this thing. And so maybe first of all, start with the stupidest way of doing that. You could attempt to just take the entire repository together with a problem and basically just copy-paste it all to ChatGPT. So you would just do like this one-shot thing. So certainly 1.5 years ago, this was entirely impossible because it would literally just not fit into the context windows of the language model. Nowadays, where we're looking at language models with huge amount of context that you can put into them, it's probably possible to do that. But still, language models get worse the more context you put into them. So probably you're not going to get, and it would be very, very, very expensive. So you would not get a realistic system and probably would also not work well. So instead, what you can do is trying to essentially mimic how humans approach these problems. And humans don't just read the entire repository from first file to last file, and then they directly write the solution. But rather, we kind of navigate around in it and perform actions. So the simplest way you could do that would be to essentially put the language model into the terminal. So you start with a little prompt. Maybe find all text files in this directory and do whatever with that. And then the AI agent, it basically takes this prompt, and the output of it might be some thoughts, some reasoning, and then an action. Like here, for example, the agent runs pwd to determine which path it's on in the terminal. And then we give back whatever the terminal would show you, like the output of this command, and we basically pass it into the same system. So what you get here, it looks very similar to a chat, right? And this is great because language models have been trained to be chatbots. That was one of their first, like the most popular use case, right? So basically, we mimic the structure of being a chatbot, except the agent chats an action, and then the response it gets is the environment output. However, and this is, we have to talk about how dated or not this is, but bash commands are hard, right? So, which is also why humans don't really like to work in pure bash. Already something like Vim is already something that's built on top of it. And it was the same when we initially tried this. If you just put the language model into the shell, it's just not going to do too greatly because already something like editing a file, when you can't use interactive things like Vim, it gets quite complicated. You can do complicated search and replace things with set and so on. But one of the biggest failure modes also when we tried that was that the agent would just cat, display an entire file. And if that file is really, really huge, then you just filled most of the context window and performance degrades. So the premise of this paper, which was called SWE-agent for the agent that we built, was around building an agent-computer interface, just how humans have specific software, specific interfaces with which we edit code. And it looked something like this. You have the language model agent. We provide it with some special commands, which are also just bash commands, but specifically engineered for the language model. So it can run any bash commands, but also some specific commands for editing files in particular. Then these commands, they just run in a Docker session, and for example, give back all the output that you would usually see, except that we also try to make it as friendly as possible for the language model, which for example means looking to that it never exceeds a certain amount of output lines or something like that. Right. So back then, so this is April 24, we saw a huge gain with giving it basically a lot of specific tools. So for example, one of our baselines there was 10% when we only gave it the shell, just let it execute bash commands. And one of the frequent failure modes, as I said, would be it would just to look at a file, it would use cat, which is perfectly normal for a human. But then if you get 10K lines back, this is really bad for a language model. Whereas these specific commands that we engineered, they would, for example, make sure we don't overrun that. And when the agent wanted to edit a file, we did some linting on it, and we didn't let through any edits that were obviously wrong. Just because we're recovering from bad edits is harder than not making these bad edits in the first place. And we basically doubled performance with that. However, since then, things have changed a lot, actually. So first of all, like this is pretty specific, but like we use a very different way of editing. We basically edit it based on line number ranges, and now like a lot of these tools that people give to their AI agents are more like search and replace functions that run under the hood. And back then, like language models were still pretty stupid, and they were doing like a lot of, I don't know, indentation errors and obvious syntax errors. So we had this whole thing about linting and blocking edits if they were obviously destroying stuff. But now, like Sonnet 4 doesn't, doesn't do syntax mistakes, or very rarely. So you don't need to, you can be even simpler than before. I would argue that still like editing, if you're developing a software engineering agent, like getting the edit function right is still the biggest part. However, and like this is going only in the last 2 months, we actually tried to remove all tools and basically did this thing which I just called the put the language model in the terminal recently. And you know what? It works just fine nowadays. So you're going to sacrifice a few percent points in your final scores, but this actually works. But it also works because people, especially people at Anthropic, have worked really hard to basically train for exactly this use case. I mean, we're going to get a little bit into that later, how you train language models to be good at that. But yeah, nowadays you can literally just do that. So the big takeaway lesson is that software engineering agents nowadays can be super, super simple. It really, it's different if you want to be state of the art or something, but this is only a 5 for a few percent points, and basically language models are just that good and have been optimized for these things. Let's look a little bit into how an agent works in a bit more detail. So you're going to have an initial prompt where you explain the mission, the strategy. You might give tips. It can be super short, though. So back more than 1 year ago, we had maybe it was 1 letter-sized page of prompt because we had to make sure the agent didn't do stupid things. So we were giving a lot of important, if a command doesn't work, don't try to run it a second time, and stupid stuff like that. No longer really necessary. Can be super brief. If you're using function calling, which is one of the things that language models nowadays offer, which is directly optimized for agent workflows, you don't even really need to explain what the function does, and it gets it itself. The second thing that we did back then, which you might still sometimes do, is demonstrations. So basically, in addition to this initial prompt, you give it, or we call the trajectory of a successful run. So you show it basically one run where an agent did something really useful and it was really successful. And you just basically paste that in with the initial prompt. I think I wouldn't nowadays do it usually unless you have to, because it also means that it might lock the agent into very specific ways of thinking and try to solve the problem exactly the same way as in the demonstration. Which is why it can be harmful, but it can be super useful if all of your, if all of the problems that you do want to solve, fall into one pattern. Then giving one successful example of solving something like this is super, super useful. Or if you're using an open source model. So most of this is from the point of view of using the current big models like Anthropic's Claude or GPT-4o, even though it's doing not so great, or these kind of models. If you're using a open source model, maybe adding a demonstration and these things can still help a lot, especially if the language models struggle with some formatting of the actions and stuff like that. But basically what happens after we have these initial prompts, there's going to be a system prompt, there might be a demonstration, then we paste in the problem that we're solving. And then basically the language model replies with a thought and an action, where thought might just be any motivation for what it's doing. We give it back the response. Sometimes we strip out things if things are definitely wrong, but mostly it's just this pattern of action, a response, action, response. All at every step are just concatenated to the prompt, which also means that the first step is relatively cheap because you just, this is your input. Then once we start adding more and more actions and output to it, like basically what we paste into the language model at every single step gets longer and longer, right? So at first, you just have the initial prompt and one action and output. Then you have the initial prompt and two actions and output. So with every step, this gets slightly more expensive. And there's some ways around that, but usually, agent runs, like the naive way would be to say that they kind of scale quadratically in costs, so not cheap. And in the end, the agent basically calls the submit command and quits and says it's done. And this is I think this is pretty much our current prompt. So it's really not long. It's literally just, can you help me implement these changes? Here's how you should proceed. Find and read code, create a script to reproduce, edit source code, try and run your reproduction script again, think about edge cases, and that's it, right? It doesn't take more than that. I think one of the most important things here is honestly this create a reproduction script. I think honestly this is where a lot of the performance of these agent runs comes from. It's that the agent has some way of checking if the solution is correct, which also means that if you have an issue that doesn't really allow it to get to a reproduction script, an agent, maybe it's just like a human, is having a hard time fixing it, right? Because you just can't check if you really fixed, whatever was wrong. I don't know, I already mentioned that, the history gets longer and longer. You can try to mitigate that. We call this history processing. Basically, at every step, you could, take a selection of all the things you pass into the language model. For example, what we did for the initial release is that we add all of these actions and outputs, and we would just strip most of the outputs except for the last 5, which really helped us to conserve context back then. Nowadays, we don't do it anymore because Sonnet 4 can just handle the amount of context, and it doesn't help, and it just makes it slightly more complicated. And also, if you're looking at our newer language models, they have caching. So every time you send in more or less the same history plus something else, this will be cheap because this part that stays the same, you pay less for it. So if you continue to fiddle with your history, you're just going to break the cache all the time, which makes it more expensive. So yeah, it depends. Like some people, like if you use, for example, cursor or something, I think if the history gets very long, they summarize the history at some point. So there's like one point where history is compressed. I think that's a useful thing to do if you're dealing with very, very long trajectories. And then, the only other ingredient that we have is, some requerying. If there's like format errors or like the language model doesn't even give you an action, then you just ask again or stuff like that, like, stopping after too much money. But yeah, basically, this is a software engineering agent. We basically now just developed one. It's pretty simple. Probably, like for a very small baseline, you can probably write one in an afternoon if you want. Okay, I think this is mostly going to skip over this. But another thing you can see is if you run the same system multiple times on the same problem, chances are, it might get it right in one of these cases, right? So if you try 100 times, the chance is just much, much higher than if you just try once. However, it's not super easy to determine which submission was correct. So I think here on the left is from the original paper. This was the scaling where we just basically did kind of best of k. So we maybe tried 6 times and then checked if any of them solved it. And you see that back then this was almost double as high. However, for most real-world systems, just trying multiple times also requires you to actually pick the solution that was correct. Because you don't have an oracle to tell you which one was right. And this is not easy at all. It might be just as hard as solving the problem if your problem solutions are as good as they are nowadays. And it's just super expensive to run. Agents are not cheap. Running them 100 times gets prohibitively expensive. So there's some people working on that. on how to classify which solutions, especially to something like this, are correct and get slightly better scaling. Honestly, my bet would be that this is not going to be a big thing, just because systems are getting better and better. So also what you gain from trying again, I think like it's getting smaller, and it just, like your price increases linearly, what you're paying, but like your solution rate just, it doesn't increase so much anymore, I think. Right, so running out of time here, but like just a few tips on how to build agents. We went through this. You take a prompt, maybe a demonstration, probably not. You add some tools for it. Like the one thing you need for a software engineering agent is like this remote code, like the sandbox code execution, right? The agent wants to execute code to test it, and you should make sure that if it does something stupid, it doesn't wreck your computer. So this is actually where most of the engineering goes in. The rest is pretty simple. Then you handle exceptions, maybe manage context, and that's it. So tips, I would say stay super simple, just because also language models are still evolving, right? So if you tune it really, really, really well to a language model that exists right now, and then 2 months later there's a new one, none of your prompt engineering might apply anymore. So, or none of your very complex scaffold that you're building might apply anymore. So I would say better err on just making it very stable, and then just wait for the next best language model to arrive. The other thing is, like it's mostly my experience, is like making experiments for these things is not super easy, and you should especially be aware that if you just try something with 50 instances, like 50 test cases, and maybe like you do some changes and gets like 2 or 3 more, it's just not statistically meaningful, and you kind of spend a lot of time just chasing these specters, because everyone kind of, like there's a big confirmation bias in all of us. So even if you know what statistical uncertainties are, and like there might be like a 10% range at 50 instances, we still want to believe, right? So this is another reason why I would say keep it simple. It's just because optimizing these things, it's expensive, it takes a lot of time. So I would rather place my bet on a few simple things that I'm trying, and then test them really well, like test them on as many test cases as I can to make sure they really generalize and aren't overfit to anything. And the other thing is, I think to optimize it, reading the trajectories, that means reading like this long sequence of actions and outputs, I think that's the best way to optimize it, because you just need to know what the agent, what the language model is doing, what it's struggling with. And the best way to do is, like write yourself like whatever you need, like as a small software to quickly browse through these trajectories and read as many as you can. All right, only having 7 minutes left. So mostly gonna flash this. We might have to skip the demo so we have time for questions. So SWE-agent, that was our system that we built originally more than a year ago. It was the first open source software engineering agent that really did something, as it solved like 20% of issues. We released it, I think, 2 weeks after Devin made a big splash with its demo. So Devin is a company that's somewhere close to here. And they were basically building the same thing in secret. We had been working on it in secret for half a year. They released 2 weeks before us. But we are open source, so I think we can claim we are like the first open source system, and then we had almost the same performance as they did when we launched. And this is still going on. So it's now 1 year later. It's still stayed roughly the same as in like the, what it really does, even though I more or less rewrote the whole thing from scratch. You can check it out. It's open source. It's very easy to configure and to hack. So maybe this is the one thing I can very briefly flash. It's a little bit small. But basically, remember when I showed you, sorry, this is the default. When I showed you the prompt, like this is the entire prompt. Now we're giving into the language model. This up here is your helpful assistant. That's a system prompt. Here we configure which tools we give it. Each of these tools is just a simple, it could be a bash executable, it could be a Python executable, really nothing special. And this is already like kind of esoteric, which is like, like when the agent submits, we can show it one more message or many more messages, like, and ask it to do a little bit more double checking or something. But so in reality, like those first 30 lines are really all you need. In addition to a problem statement. And so when you run it, it looks something like, oops, that's wrong. Looks something like this. It's going to start up. It's basically spinning up a Docker container. Here it says environment initialized, and it's uploading basically our tools, which are single executables. It's going to copy them into the container. I'm not sure if I have internet. Oh yeah, okay. And now you see we basically pasted in this initial prompt, and now the language model proposes as actions, like looking at this directory, and then we just continue, like waiting for it to give us actions. We execute it, them, show them the output, and so on. And it's going to continue to do that. And like there's there's a lot of things you can do. For example, you could try to just remove all of the tools, see if it still gets it solved, which it probably will. You can even get rid of most of these instructions, and it's probably still going to do relatively well. Partially, I think, because of this is with Sonnet 4, and it's just tuned to this kind of task. All right, so I'm going to run through a couple of these things. Including the implementation, which is sad. There's also a batch interface, which I didn't just show you. If you have like 1,000 issues or you're evaluating on a benchmark, you can just spin them all up in parallel. So the last thing, and this touches our most recent project, is so far we've only talked about, like, basically we had models as a black box, and then we added some prompts to them, and we added some like scaffold around them to basically make them iterate. The other question is like training language models. And so there's usually 3 different stages to training. We have pre-training, which is super expensive, and you just have this huge amount of uncurated data, where the language model is just trained to predict the next word, and we imbue the model with knowledge. And there's fine-tuning, which is the same thing, except that we have like a super small amount of data, but it's very highly curated. And we can shape the output and have it long thoughts and these kind of things. And then there's reinforcement learning, which is dark magic, and this is all what I'm going to say about it. And so historically, like a lot of people, when they're thinking about agent performance, they are thinking a lot about reinforcement learning, where you basically give rewards for completing a task. However, fine-tuning actually works remarkably well for enforcing, for shaping models. And you can relatively easily fine-tune, let's say, a 32 billion model if you have, a couple of H100s and a day to spare, or like a day of runtime. This is enough to fine-tune a 32 million parameter model to be a good agent. The only thing you need to have is good data. Which means basically kind of similar to the demonstrations that we were talking about. Like, you need examples for the model to see how to successfully solve something. And this will be the hard and expensive part. Reinforcement learning is maybe even more expensive, but like fine-tuning, basically getting the data is what's difficult. Fine-tuning is pretty simple. So I only have 1 minute left, so I'm going to skip through this. But basically, we had this project called SWE-Smith, where we generated a lot of synthetic problems to solve, then had like thousands and thousands of agent trajectories, and then we fine-tuned a small 32 billion model called Quen 2.5, which by itself, at the beginning it has like 10% performance on SWE-bench, and we fine-tuned it, and it got to 40%, which at the time where we released was the best open source model for SWE-bench. Outperforming actually even GPT-4o. So you can, basically bottom line is fine-tuning works super well. It's still going to be a lot of effort in getting the data. All right, so summary, running out of time. This bomb will soon explode and switch to red, I guess. So SWE-bench, challenging benchmark, even though, it's like progress has been so crazy that it's We're looking at 70% success rates there already. If you want to build an agent, keep it simple. You can stay simple. Read lots of trajectories to find out what doesn't work yet. If you run experiments, be aware of fluctuations and everything. Just make them big and meaningful. If you want to check out our projects, they are all on GitHub. You can go to, unfortunately, all of the URLs are cut off, but if you Google SWE-bench or SWE-agent, you're going to find them. Open source, easy to hack. Maybe not the most user-friendly because we're an academic project, but they are easy to run, I think. And they're the easiest ones to experiment with, I think. And finally, the last thing I talked about was this project about generating large-scale fine-tuning data, which I guess this will take you some time to get into. But if you do, or you have a very specific company thing that you want to train agents on, I think this is a cool way to do it. All right, so the time is at 0. I don't know if that means we have no time. Oh I see, okay, no questions. I mean, you can find me afterwards. And I'm happy to answer anything here in the hallway or something. Thank you so much.